Okay, good afternoon, respected Professor G.H. Kaisar and all other respected guys gathered here. Here I am Doke Arvind Maram. I am pursuing PhD on the research title Rare Earth Global Soft Correct Nanoparticles, Low Temperature Synthesis, Microstructural Super Exchange Interaction, and Dielectric Characterization at Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. Under the guidance of Professor G.H. Kale, Department of Electronics, YC College, Tuljapur District, Usmanabad. My research center is Sri Krishna Mahavidyalaya, Gunjoti, Umargad. Initially, I prepared literature survey. Initially, books prepared like there are the element acetinides, pinch of Windows and Peterson, introduction of solid state physics by C. Keeter, and introduction of electrodynamics by David G. Griffith, etc. And prepared, improved, prepare and referred and improved the concept like dielectric constant, electric susceptibility, polar and non-polar dielectrics, linear dielectrics, non-linear dielectrics. Permeability, magnetic susceptibility, saturation magnetization, spin interaction energy, studied rare earth ions, their electronic configuration, ionic radii, and calculate their magnetic dipole moment theoretically. And also studied the iron group or transition metal ions. In this slide, here I studied theoretically rare earth ions with their electronic configuration, magnetic dipole moment, and some concept about it. Here, the interesting point about the rare earth ion I got is that the radii of the trivalent ions contradict fairly smoothly as well as go through the group from 0. Sorry 1.11 angstrom unit at cerium to 0.94 angstrom unit at yttrium. This is the famous lengthened contradiction. It means that as we go from cerium to lanthanide, the atomic number increases, but the radii of this rare earth ions is goes on decreases, although their atomic number is increasing. This is the interesting fact I understand during the literature survey. And here studied some transition metal ions and their magnetic dipole moment. The magnetic dipole moment is calculated in terms of Bohr magneton, and for transition metal ion, we can simply calculate the magnetic dipole moment using formula under root n into n plus 2, where n is the unpaired electron. Instead of this formula, we can use the formula to find out the magnetic dipole moment in terms of Bohr magneton. That is uh, that is G into under root J into J plus 1. But in case of transition metal ion or rare earth group ions, the angular momentum is vanishes, or it take a or it does not take contribution for the angular momentum as well as magnetic dipole moment. It means that it vanishes. Therefore, the magnetic dipole moment can be find out for the transition metal ion using formula 2 under root s into s plus 1, where s is the spin angular momentum. It means that here I I I want to say that the uh, magnetic dipole moment can be find out using two formulas, that is 2 under root s into s plus 1 instead of this 2 under root j into j plus 1. Here j is the total angular momentum. Here we no need to take the angular momentum because it vanishes for the transition metal ion. Or another formula is here, that is under root n into n plus 2, where n is unpaired electron. Here, in this slide, I was theoretically studied and calculated the Bohr, uh, the magnetic dipole moment for in terms of Bohr magneton for transition, for some rare earth ion like cerium, yttrium, or other some dipole gene. Next, from some journal like Symmetry, Material Literature, Journal of Physics and Chemistry of and Journal of Magnetism and Magnetic Material, to understand the goal of characterization and application of ferrites. XRD, to find the lattice parameter, particle size and crystalline size. FTR, this characterization is to verify the elemental composition, bond length, crystal structure. Same, that is scanning electron microscopy. This characterization is taken for surface morphology and study the particles. So, same is transmission electron microscopy. This characterization is taken for size, shape, and structure as well as purity of the sample. VHM, this characterization is used to analyze the magnetic properties like magnetic susceptibility, saturation, magnetization, porosity, retentivity, and to verify the magnetic nature, whether the particles are uh, or hard from the hysteresis loop, and to study the hysteresis loss. In this slide, some application of ferrites are mentioned here. These applications are usually of the soft ferrites. Because of some unique properties of nanocrystalline spinel ferrite, material is its ferrite material, its importance in industry and technology increases. Demand of soft magnetic material increases due to its improved performance in electromagnetic gadgets, memory, data storage devices, sensor, etc. Nowadays, a major photo major photo catalytic activity enhancement of spinel ferrite nanoparticles are received. In this slide, some types of some types of ferrites are mentioned here. According to crystal structure, ferrites are classified as spinel. The spinel structure is also cubic structure, hexagonal ferrite, garnet ferrite, and orthorhombic ferrite. According to porosity, the ferrites are classified as soft and hard ferrite. Soft ferrite has low porosity, hard ferrite has high porosity. Now again, spinel ferrite. Again, there are tips. Normal ferrites. Sorry, normal spinel ferrite, inverse spinel ferrite, or random mixed spinel ferrites. Method of preparation. The different method like soldier chemical bath method, ceramic method was theoretically studied for the synthesis of ferrite nanoparticles. Of this, out of this, we all selected the soldier method because of it is easy and low cost. The soldier is more chemical method for the synthesis of various nanostructure. In this method, molecular precursor, usually metal oxide, it is dissolved in water or alcohol and converted to gel by heating and stirring by hydrolysis or alcoholysis. This is obtained by this obtained gel wet or damp, it should be dried using appropriate method according to desired properties and application. For example, if it is alcoholic solution, the drying process is done by burning of alcohol. After the drying stage, uh, produced gel is powdered and then calcinated. The solution method is conventional and industrial method for the synthesis of nanoparticles with different compositions. Solid method work temperature since there is good control over the chemical composition of the product. After the drying stage, produced gel is powdered and calcinated. Here, from some research paper, some literature review is taken that is about nickel zinc ferrite. And zinc ferrite is a normal spinel ferrite cubic with a divalent Zn cation occupied the and trivalent Fe ions occupied the tetrahedral. Nickel ferrite has inverse spinel ferrite with the divalent nickel cation occupied the tetrahedral side and trivalent Fe cation octahedral sides and partially in tetrahedral sides. Zinc ferrite has low saturation magnetization and high coercivity because dimagnetic divalent Zn cation occupied A side and trivalent Fe cation occupied B side, which leads there is weak AB superexchanging interaction. If the divalent Ni cation inappropriate amount doped in a Zn ferrite, result that it increases the saturation magnetization and increases the coercivity of nickel zinc ferrite. If doping if doping concentration of zinc increases and concentration of nickel decreases, saturation magnetization decreases and vice versa. After that, I select the series for the synthesis of my sample. That is neodymium soft ferrite and eurobium soft ferrite. There's some basic information about the element that I had taken for the synthesis or to make the nanoparticles. Using this formula, I I calculate the sample weight for the synthesis. In this slide, synthesis method is mentioned during the synthesis of my sample. All weighted compounds were dissolved in 250 ml distilled water solution were stirred with 144. Sorry, here 444 is, but still with 144 RPM with heating about 1 hours and simultaneously 7 pH by adding ammonia. It is observed that the amount of ammonia increases in step in each sample with increase of rare earth amount. Once the solution we are going to take to viscous mode, it is kept on hot plate for half an hour and finally start the auto-combustion method. Before heating all the solution sample were grinded for half an hour. All sample were heated at 10 degrees Celsius for sintering for 6 hours using Merkel furnace with 3 ampere RMS current. After heating the sample, we grinded for half hour. Finally, the uh, nanoparticles were these are the final product. Here is a video of the uh, auto combustion. Some features of during the synthesis, that is grinding, heating, and final product. From XRD data, intensity versus 2 theta graph plotted using the origin software conclude that there is no impurity or secondary phase. From FTI characterization, it taken for the analysis of chemical composition and bond length, higher and lower wave number side absorption peak reveals that the development of spinel cubic structure at both octahedral and tetrahedral side. The graph of this characterization is mentioned in this slide. That is the XRD intensity versus 2 theta graph. This is second series. This is the FTR graph of first series. Thank you, sir. Thank you very much.